on to our next speaker, Professor Deep Jariballa. Professor Deep Jariballa, are you there?
Yes, I'm here. Can you see my screen?
Yes, I can see your screen. So
Can you hear me okay?
Yeah, it's good. Let me introduce you briefly.
Sure.
Professor Jariballa is an assistant professor in Department of Electrical and System Engineering at University of Pennsylvania. He completed his undergraduate degree in metallurgical engineering from Indian Institute of Technology, BHU, in 2010. And he received his PhD degree in material science and engineering at Northwestern University. So after then, he started his postdoctoral research fellow at Caltech University. And then he joined as a University of Pennsylvania in 2018 to start his own research group. So he's gonna talk about low dimensional heterostructure for advanced logic and memory devices. Professor Jariballa, please go ahead.
Okay, thank you, Professor Lee, for that kind introduction. I would also like to thank the organizers, especially Professor Kim and Professor Joo-Hoon Kang, who invited me over here. This is really a great opportunity for me to present. And so as the title says, I'll be talking about low dimensional heterostructures. Then you'll quickly see that the heterostructures are mostly involve two-dimensional materials as a primary component. So as I get started, let me give a very brief overview of my research lab. Ours is a relatively young research lab. We have been operating at University of Pennsylvania since 2018, and we are sort of broadly divided into four major research areas. The first one being nanoelectronics, where we look at logic and memory devices. Then we have a lot of research going on in nanophotonics and optoelectronics. And then finally, there are two more areas where we have presence, which is mainly functional imaging. This is both scanning probe as well as electron beam imaging. And finally, some growth and synthesis, and this is mainly metal organic chemical vapor deposition of sulfides, and we're now also getting into nitrides. So my focus, or the focus of this talk, because of limited time and everything else, is going to be this right here. And I'm going to be talking about some logic and memory devices. So the way our group likes to think about this research challenge in modern classical computing is the following. Now, I understand that quantum computing and quantum information science are very popular these days, and a lot of people are working very intensely in those areas. But we think that classical computing is still very, very important because everything operates on classical computing, including the reason we are having this online conference. And there are still major challenges to be solved in classical computing. Out of them, the two major challenges are as follows. First of them is the power consumption problem. As devices shrink smaller and smaller, the steady state power consumption keeps rising up. And so you can see here the power idle in watt of various microprocessors with increasing sort of complexity or sort of more progressive generation of processors. And you can see that the power idle keeps increasing, right? This is not good, clearly. Likewise, there is also another problem, and the second problem is more created by the first problem. And because we have powerful processors, our computing needs have expanded. The internet has born. Everybody holds 5 computers. You have a iPhone and a iWatch and iPad and also a desktop computer. Everybody has many computers. Everybody uses social media all the time. This generates vast amounts of data. And so to process this vast amounts of data, there have been a large explosion in sort of machine learning and AI algorithms, right? And most of these algorithms are memory intensive. In other words, they require vast amounts of memory for computing. Okay, so this creates a bottleneck of shuttling data between the CPU or the control processing unit or central processing unit to the memory unit. And this back and forth of shuttling data actually slows down the computation. And it not just slows down, but it also further increases the power consumption. So in some ways, one problem led to the other problem, and the other problem is connected to the first problem because it also leads to higher power consumption, right? And so you can think about that this is sort of a power consumption problem more at a device level, and this presents more of a power consumption problem at a circuit level. But they are really both are very important problems. And why are they very important problems? Well, because if we keep going the way we are going in terms of consuming data using the internet, we will basically start consuming most of the energy produced by humankind for our internet and computing purposes. And this can be seen from the energy forecast that various agencies have been making, and that about 21% of of the total electricity produced by 2030 would be consumed for IT and communication and computing purposes. And likewise, it is expected that if you continue along this trajectory by 2050, all of the electricity produced by humankind would be required only for IT purposes or computing purposes. This is just unsustainable. We will burn off our planet very quickly. So we need to find a way to do computing more efficiently. Okay, so then, let me take a little bit of a jump and talk about, where we are in terms of computing and where do we want to go. Now, clearly, current microelectronics rely on silicon, right? And silicon has been very, very successful in terms of in terms of computing. And one of the reasons silicon has been successful is because of its highly passivated surface that has been achieved, right? And so here is where I'd like to jump into the material science of things. And the reason silicon devices have operated so well is because the surfaces and interfaces have been optimized very, very well. And this reminds me of a favorite quote by Wolfgang Pauli, who said, "God made the bulk, surfaces were invented by the devil." Wolfgang Pauli, I believe, is the same person that the first speaker today introduced, saying that semiconductors are not great, nobody should be working on them. Turns out, semiconductors work great, and they are the basis of all modern microelectronics in computing. And the most modern silicon transistors, if you look at them, they are FinFETs. And these FinFET transistors clearly have very nice and passivated surfaces and interfaces. And because you have nice passivated surface and interfaces, combined with the fact that you have these nanostructured or really thin pillars, you can achieve very low power consumption. It gives you very good electrostatic control over the devices. Okay. And so the question really is, or the big engineering challenge which is in front of us is that we have to produce passivated and defect-free surfaces and interfaces for high-performance semiconductor electronics, particularly with regards to high efficiency and low power consumption. And so in this regard, actually, two-dimensional materials are actually very popular, and they are very promising too. And so, I think two-dimensional materials were introduced by earlier speakers today, so I don't want to spend too much time introducing them, but I do want to say that they are available in a variety of electronic flavors, right? So you have the semi-metallic graphene, you have hexagonal boron nitride that is insulating, and then you have the transition metal dichalcogenide that are semiconducting. And there are many other more varieties. There are topological insulators, ferroelectrics, ferromagnets, charge density wave materials, superconductors, etc., etc. But the most important thing about them is that they are freestanding, stable, and passivated materials, right? So now, if you consider from the materials perspective, as I was telling you on the previous slide, you no longer have to worry about this passivating surfaces and interfaces. And this makes possible a large variety of new devices that you can make with really novel functions. And this has sort of given birth to the field of van der Waals electronics, where people have started, stacking various flavors of 2D materials one on top of the other without the need of lattice matching or epitaxy. They're now even twisting them to introduce new exotic electronic properties. And so the question that we like to pose in our lab, and sort of the whole talk is in many ways based on is how can van der Waals interfaces and two-dimensional materials give us unique advantages in post-Moore's law electronics. Now, clearly, Moore's law has come to an end. The question is, what beyond Moore's law are these new materials and interfaces going to bring about the next revolution? And that's the central question I want to ask, right? And so our vision in this is that, three-dimensional materials such as silicon, gallium arsenide, silicon germanium, they have stayed with us for several decades. And I think they are the basis of modern technology, and you cannot get rid of them. Okay, so three-dimensional materials are always going to be there. The question is, what happens when you start integrating 2D materials with 3D materials? Do they give you any interesting advantages? Can you exploit new opportunities? And this is where we are exploring two different kinds of devices, which I will be talking about. One is a tunneling field effect transistor, and second one is a ferroelectric field effect transistor. One is a logic device, other is a memory device. Now, you may ask me, what are the advantages, or why do you want to integrate 2D with 3D? Well, I gave you the more commercial reason, which is that 3D materials are the basis of everything. You just can't get rid of them. But there are sort of technical advantages too, and which is one of them is gate tunability. 3D materials are bulk, they are thick. 2D materials are very thin, so you can electrostatically have much larger control over them as opposed to 3D materials. Conversely, in 3D materials, we know how to do substitutional doping really well. So you can substitute, phosphorus, boron, and silicon, or other 3,5 with various concentrations very well. In 2D, this is quite hard to do. In fact, still people keep searching for P-type 2D materials, and they are not very easy to find with high mobility, right? And finally, there is interface engineering. If a 2D material can be used to passivate a 3D material surface, right, then that would achieve the best of both worlds together, and you would not need to re-engineer the 3D interface. So this is where we have been experimenting for some time now by using 2D molybdenum disulfide, tungsten diselenide, also materials like black phosphorus and indium selenide, and integrating them directly with silicon in the hope of making a heavily doped PN junction and gate that heavily doped PN junction to make a tunneling field effect transistor, right? And so here is an example of how there is a 3D semiconductor wafer, which is silicon in this case. This is heavily P-doped. We open up a window in the oxide, and we stamp a 2D layer on top of it. Then we grow, we pattern, electrodes over here. We coat ALD dielectric and put down the top gate. So basically, this is how the devices look like. Here's an optical micrograph. Here's an SEM. Here is a band diagram, and the band diagram tells you that all the depletion width is essentially in the 3D material right here. Sorry, in the MOS2, which is a 2D material. And as you apply a gate voltage, this depletion width can shrink or expand, thereby leading to exponentially large tunneling currents going from here to here, right? This is the basic principle behind it. And so this works both for Scotch tape exfoliated material as well as large area CVD material. It works with mono layers as well as few layers. We have tried all combinations. Much of it is shown in this paper that was published last year. And what you can see is that when you operate this device, you can use it it works like a diode. Of course, it's supposed to be a PN junction diode. But then when you reverse bias the diode and vary the gate voltage on top, you can change the reverse saturation current by orders of magnitude. As I was telling you before, this orders of magnitude change in current is mainly the tunneling current, right? And so if you put a drain bias over here and scan the gate bias, you'll get a very nice transistor property. But if you do it over here, you will get very little modulation of current, because here it's mostly diffusion current, and diffusion current cannot be modulated. So this acts more like a constant current source under forward bias. And so you can clearly see over here that not only you can get high on-off ratio, but you can also get high rectification ratio, right? So in other words, we have a same 3-terminal device that can be a tunable diode, a constant current source, as well as a logic transistor. And so about 30 or 40 years ago, there used to be a concept known as diode transistor logic. That concept was abandoned because transistor logic took over, and it was faster and more efficient than diode transistor logic. Now we have these kind of devices that can be both diodes and transistors at the same time. And so we are trying to think about reconfigurable logic circuits using these kind of hybrid devices which act as both diode and transistor, depending on how you bias them. But what I'm not showing you here, and you might be wondering that I was talking about tunneling, where is the steep subthreshold slope, right? The steep threshold slope should matter, right? I want to mention that these 2D, 3D combination actually can actually give you some of the highest rectification ratio and on-off ratio concurrently in these type of in-depth combined devices. And again, because of shortage of time, I'm not going into too much detail, but I want to show you some piece of unpublished data that we will soon be putting up online on arXiv. And that is, if you choose the right material, in this case WSE2, with p-type silicon and engineer the interface properly, you can get actually this heavily doped p and heterojunction where you can modulate it strong enough that you can get sub 60 millivolt per decade switching slope, right? So 60 millivolt per decade, this line over here is supposed to be the thermal limit on which thermionic transport or thermally controlled transport occurs. If you are seeing switching below this thing or below this value, or in other words, your slope is steep enough, then you are going to have tunneling currents happening, which is what we're seeing over here. And so we are quite excited by this. There is still a lot more work to be done, and I think we have a lot more data to show, but I'm preserving it because we have not submitted the paper yet. But in other words, what I wanted to say is that it is possible to combine this 3D silicon and heavily doped and 2D material, and then tune the 2D material to actually get steep subthreshold tunneling field effect transistors. So now let me move on to the next problem. And the next critical problem that I want to address is that of this logic and memory, the bottleneck, right? And this is famously known as a von Neumann bottleneck, right? Because this type of computer architecture is known as von Neumann computer architecture. Now, to actually reduce this lag of shuttling data between the memory and the logic, you want to have the memory very tightly integrated with the logic. In other words, you want to have the memory devices sitting right on top of the transistors, right? And this is something a lot of semiconductor companies have been thinking on very strongly, including the semiconductor giants in Korea, such as LG and Samsung. And so here's the game for this, right? This is how a modern microprocessor looks like. The bottommost layer is your silicon-based transistors, and all the above layers are basically interconnects, right? So this is your front end of the line or transistor layer. And then you have the back end of the line, which is basically the interconnect layers. Now, the idea is you want to integrate the memory devices in these back end of the line layers. The problem is, once you make front end of the line, there is a thermal budget assigned. The thermal budget is about 400 degrees Celsius. So you want to make the back end of the line layers within 400 degrees Celsius thermal budget. Otherwise, your front end will get destroyed and it is pointless, right? So the key to making back end of the line integration of memory devices or MEMS devices or photonic devices that you need low temperature processes. At the same time, you need high quality materials at low temperature processes. This is hard to achieve. This is thermodynamically a huge challenge for material science, right? A lot of times material science want high quality materials, but they have to go to high temperatures for that. This is not easy. But we have been fortunate in finding one such material which can be deposited at low temperatures, and that is also ferroelectric in nature. And this material is scandium doped aluminum nitride. This was discovered in 2019, so it's very new material, right? This combined with 2D material, and the advantage of 2D material is it can be transferred at room temperature on any material you want by wafer bonding. You can now think about a low temperature back end of the line compatible assembled high performance memory device. Now, why do I call it high performance, and what is this ferroelectric memory device? So the device that we are targeting is called ferroelectric field effect transistor. So it's just like a regular transistor, except the dielectric is ferroelectric in nature. In other words, it can store charge even if you remove the voltage. It can store a positive charge or a negative charge even if the voltage is removed. So just like a magnet, but in the electric field, right? So electric field can store polarization in it. And as you can see from these curves, it is nearly ideal ferroelectric. It has perfectly square or rectangular shaped loops, right? So this is very exciting for us. And if you compare the metrics of this FE-FET, right, in terms of right energy, right, and right speed and right current, this is where it has a huge advantage in terms of power consumption and speed as compared to all the other non-volatile memory technology. And so our goal was to basically use this two-dimensional channel on top of aluminum scandium nitride and make this ferroelectric device. We have successfully made this. This was also published just 2 or 3 months ago in Nano Letters again. You can look this up. We put MOS2 on top of aluminum scandium nitride grown on platinum, which is grown on silicon. All of the processes involved over here are 350 degrees Celsius. So it is in the back end of the line budget. And you can see that the transfer characteristics are very nice, almost nearly square shape hysteresis loop, and it is counterclockwise hysteresis loop, which again tells you that it is ferroelectric in nature, right? But nobody believes you that you have made a memory device until you show endurance and retention. So we have done some endurance measurements, and the devices are stable up to at least 10,000 cycles, maybe even more as you cycle them. And then if the charge state, which is the high, which is the low resistance state and high resistance memory state, right? They can be stored for at least 10 to the power 5 seconds. So this is actually very, very advantageous. Now, in terms of transistor-based memory, there are two major metrics that you want to compare. One is the memory window, another is the on-off ratio. And so in memory window, we are normalizing it because everybody makes different thicknesses of the dielectric. So you can see that the normalized memory window and on-off ratio metrics, this 2D ALSC FE-FET is actually better than anything else that is out there, right? And this number has actually been pushed even further. We have unpublished data where we have 10 to the power 8 on-off ratio, and the memory window normalized is still similar. So we have been able to push this point at least 2 more orders of magnitude this way. So to further prove this is still a ferroelectric switching effect, we made similar devices, but on just aluminum nitride, not on aluminum scandium nitride. And we were able to see hysteresis in them too, but this was clockwise hysteresis. Clockwise hysteresis means it's simple charge trap based hysteresis. Counterclockwise hysteresis is actually more for ferroelectric switching. The other thing to notice is that the switching slopes in the ferroelectric FETs actually very, very steep. Right. In fact, if you look at this one, the switching slope is very steep, about 100 to 120 millivolt per decade, as compared to about 3 volts per decade for aluminum scandium nitride. This further tells you that you have this ferroelectric switching going on, which produces an effect known as negative capacitance. And this negative capacitance effect can give you this kind of very steep switching behavior. So the other big question we want to ask and answer is actually, can you make these ferroelectric films thinner, right? Because if you look at the operating voltages over here, they're still not good. They are a few tens of volts. So we have succeeded in making thinner ferroelectric films. These are about 20 nanometer thick films of aluminum scandium nitride. And in these films, there are no more 2D materials here. This is just simple MIM device. And this MIM device acts like a ferroelectric memristor or ferrodiode memristor, however you like to call it. So it's like a diode, but beyond a certain applied electric field, the ferroelectric polarization switches and the diode polarity switches. Okay, so you get large hysteresis in diode operation. And this stays in a non-volatile way, which you can use for memristor or other memory applications. Once again, it can be cycled many times. It can be, it remains quite stable up to several thousand seconds, actually. This was also published just 2 months ago in Applied Physics Letters. In fact, this paper has attracted attention of major industries, including Applied Materials, Intel, Samsung. Everybody has reached out to us for this. And one of the main reasons why it is so attractive is because compared to hafnium zirconium oxide, right, or other ferroelectrics out here, its CMOS compatibility is very high, and it concurrently has a high on-off ratio combined with high CMOS compatibility. And so this, with some amount of optimization, this can be you can actually think about putting this into foundry processes, and therefore a lot of industry is excited about this. Final question that I want to mention is that, about switching. A lot of people are interested about switching speeds. So we have actually done switching speeds measurements, and we have seen about 200 nanosecond. Switching has been observed using PUND measurements. So PUND stands for positive up, negative down measurements. And in this case, we send a fast pulse through the ferroelectric, and we measure the current flowing out as a function of time. And we see that this ferroelectric current peak actually is about 200 nanoseconds in width, and therefore we conclude it's about 200 nanosecond switching. And so this is sort of the big picture or future vision that I want to project, is that using two-dimensional materials and these ferroelectric materials and making heterostructures with the 2D and 3D materials, you can think about the next generation of logic chips that involves this tunneling field effect transistors that are low powered. But then you can also think about memory devices that are built directly on top of logic devices, all with back end of the line processing. And these can also be with 2D materials or without 2D materials. And you can have a combined memory logic chip working together for these high performance machine learning and AI applications. And we have a lot of unpublished data on this. I'm preventing from showing it now because we still haven't filed patents in this area, and this is a very sensitive area, but I'm happy to discuss more if you want. So here is sort of the big summary that I wanted to throw out, that direct integration of 2D semiconductors with 3D semiconductors has, or electronic materials, has potential for transformative logic devices as well as memory devices and other architectures. And these ferroelectric field effect transistors and ferrodiodes are both extremely promising for 3-terminal and 2-terminal low power, high speed memory, and even for neuromorphic computing applications. So I was told by Professor Kang to give a couple of pieces of advice to younger researchers. So I think during my introduction, Professor Lee already covered my academic journey quite well. I started from Banaras Hindu University. My degree was in metallurgical engineering. So I learned about iron and steel making, but then I did summer research at Rice University where I learned about graphene synthesis. Then I went to Northwestern University and did PhD in material science. Actually, I was colleague of Professor Joo-Hoon Kang, and I was working on electronic devices there. Then I went to Caltech and did photonic devices in applied physics. And now I am a professor of electrical engineering. So I jumped many, many fields. Every time I changed institution, I jumped fields. And I think there is some lesson to learn over there. And my advice to younger researchers and younger scientists, both in Korea and everywhere around the world, is that when you are young scientist, young researcher, read a lot of literature, and don't just read in your area of research, but read a little bit outside your area of research. Broaden your horizon, broaden your knowledge, attend a lot of talks and attend a lot of conferences, and again, attend them slightly away from your research area. Therefore, you will get new ideas, you will learn new things. Always have a side project, a side idea that is not your main project, but you work on it few hours every week, and maybe it leads to a big breakthrough. And always think about big game-changing problems that will change the course of entire science and technology, and put your research in those perspectives and think about it on a periodic basis. And finally, don't be afraid. Collaborate a lot, get into new areas, unfamiliar areas of research, and don't be afraid of any new challenges you face, and you will be successful eventually. So that's my 2 cents of advice to all the young scientists. And finally, I would like to thank all the hardworking students and postdoctoral scholars in my lab. We have a large contingent of Korean students and postdocs from various universities, and they are all excellent. And so I'm very happy always to interact with the Korean academic community. And finally, number of collaborators again from Korea, from various universities, as well as several funding agencies that support our research. And finally, thank you all for your attention and the invitation, and I'm happy to take any questions.
Okay, thank you very much for really nice talk and constructive comment for the young scientist, Professor Jariballa. Probably we can have one quick question from the audience. Is there any question from the audience?
Yeah, I have a question.
Yeah.
Okay, please go ahead.
Yeah. Hello, Professor. I have a question.
Yes.
I have a question in this the direction of the transfer characteristic loop. As you have mentioned, anticlockwise is the evidence that it is a ferroelectric memory. Is there any direct relation between the anticlockwise loop of P and the transfer characteristic?
Yes, it is. And this is true, but you have to understand this is true because this is an N-type semiconductor channel. If you make it a P-type semiconductor channel, the hysteresis loop for a ferroelectric FET should be clockwise.
Okay. Okay.
Okay, so in the n-type case, because the conduction happens as the Fermi level moves up in the conduction band, right? And Fermi level moves up in the conduction band when the ferroelectric polarization is up, right?
Yeah.
And so because these two are connected, the ferroelectric hysteresis loop and the transfer characteristic of an n-type FE-FET should both have anti-clockwise transfer or anti-clockwise direction. But for a p-type or whole conducting channel, it should get reversed.
Okay.
Does that make sense?
Yeah. Understood.
Professor
Thank you.
Lee, thank you for your presentation. And I have one more question.
Sure.
So, what is the role of the oxide in the FE-FET structure?
Okay. Yeah, it's a very good question. Actually, the reviewers harassed us a lot on this. The role of the oxide, I mean, at least what we have found is that it does not play any major role. This is native oxide, by the way. So this native oxide is non-ferroelectric in nature, and I think it is mainly aluminum scandium oxide. Now, when the oxide is maybe just 2 to 3 nanometers, it is not a problem. But when it becomes thicker, the memory window actually reduces. Ideally, we want zero oxide. So what we are doing now is we are making a metal insulator, metal stack, and right before deposition of the 2D material, we are etching the top metal. This way, we have been able to get almost sub 1 nanometer oxide, and so the memory window stays as wide as possible.
Thank you. Thank you very much.
Okay, thank you again for the nice presentation, Professor Jariballa.
Thank you.
Let's move on to our last speaker in the morning session, Dr. Sung-In Hong. Are you there, Dr. Hong? Dr. Hong, can you hear me?
Yes, I can hear you.
Okay. Dr. Hong is working in the University of Texas at Austin. He's gonna talk about transition metal dichalcogenide and their photosensing applications. Dr. Hong, please go ahead.
Thank you. First of all, thank you very much for giving this good opportunity. It is an honor to be here. The topic of my presentation today is transition metal dichalcogenide and their photosensing applications. Before we go any further, please allow me to introduce myself. This is Sung-In Hong. I studied electrical engineering and material science and engineering in Korea. Currently, I've been working as a postdoc in the University of Texas at Austin. My research interests and experiences are synthesis of 2D materials, high-performance devices, neuromorphic engineering, and photosensor applications. But enough about me. I would like to divide my presentation into background of transition metal dichalcogenide as the next generation semiconductor, TMD-based photosensor applications, and summary. What is next generation semiconductor? Next generation semiconductors are semiconductors that include new functions such as artificial intelligence or have significantly improved power consumption. To figure out why the next generation semiconductors are needed, we should understand a semiconductor paradigm first. The semiconductor technology have been developed dramatically since the Moore's law era in 1990s. Through the era of mobile convergence and digital convergence, we are living in the IoT era, and the era of artificial intelligence is approaching. So why do we need a next generation semiconductor? Gordon Moore, who founded Intel, said in April 1965, the semiconductor performance will double every 24 months. Until 2010, this law have been fairly well followed, but this law comes to an end when the integration is no longer available. Currently, the performance of the semiconductor has encountered to the physical limitations. Another problem is that we living in a 5G era need more and more data. This caused a rapid increase in the amount of data center. As a result, we need more power. This made us find a new solution. In other words, the limitation of conventional semiconductor technology have made it very difficult to achieve higher integration, higher speed, and lower power. So next generation semiconductor are essential to overcome these issues. So today I would like to introduce 2D transition metal dicalcogenides as the next generation semiconductors. After the discovery of graphene, 2D transition metal dicalcogenides have been intensively studied. The formula for TMD is the MX2, and one layer of TMD transition metal atoms is sandwiched 2 layers of chalcogen atoms. Unlike graphene, TMD has proper band gap, so it has semiconducting property and show high carrier mobility, transparency, and high flexibility. So many researchers are actively working on electronic devices, photonic devices, and energy storage. So far, we have looked into the background of the transition metal dicalcogenides. Based on this, I would like to introduce transition metal dicalcogenides based photosensing application. The first application is about an image sensor array. We developed a 2-step growth method for large area TMD, which is the deposition of MOS2 using sputter as the first step, and then surprization in CVD as the second step. We could get the large and uniform film. As you can see the TEM image, this film is bilayer MS2. Based on this bilayer MS2, I fabricated an image sensor array. This array is an 8x8 active matrix structure consisting of switching transistor and 4 transistor in 1 pixel. If you look at the electrical properties, the on and off current ratio shows very good performance over 10 to the 5, and the average field effect mobility of the 64 switching transistor is about 4.85 centimeter square per volt second. The optical characteristic of the array shows the good performance under red, green, and blue illumination light, and the photo responsivity, detectivity, and photosensitivity were extracted, which are important figures of merit for photosensing. And this for responsivity is world recorded. In images characteristic, RGB light were uniformly detected on 64 pixels, and we can get the total image without any simulation or external circuit. This study is published in Nature Communication in June of this year. Second application is about neuromorphic engineering. Von Neumann architecture is a computer architecture developed by von Neumann, and almost all digital computers still use this architecture. This is separated into CPU and memory, but the von Neumann architecture is no longer efficient structure because of advances in technology. So we we need a new computer architecture. The solution is in our brains. Because our brains are supercomputer, neuromorphic engineering can dramatically reduce the hardware size and power consumption by emulating the nervous system. The neuromorphic devices is transistor or electronic circuits can emulating the behavior of biological synapses. The synapses is the connection point that passes neurotransmitters from a presynaptic neuron to postsynaptic neuron. I would like to show you my research related to it. I fabricated a neuromorphic phototransistor emulating dark adaptation based on perovskite TMD hybrid structure. If you can see the transfer curve on short-term illumination, the current is just increased like this. In contrast, under long-term illumination, the current under only red illumination light is decreased over time. This is very similar with Schumann dark adaptation. This mechanism is because of phase segregation of highlight perovskite. When we illuminate continuous visible light, the region under illumination will be a Brom-rich region. That means the energy band gap will be widening. This mechanism can be more clearly by using the band diagram under short-term illumination and long-term illumination. So under banding, that is very similar with human dark adaptation, and we propose potential applications such as capsule endoscopy using our neuromorphic phototransistor. The third application is about ternary circuit. The ternary semiconductor is ultra low power semiconductor device and circuit technology that utilize states 0, 1, and 2. In comparison with bilayer semiconductor, the ternary semiconductor can achieve the superpower saving, miniaturization, and high performance features. I would like to show you the relate to it, my research. I fabricated heterojunction transistor based on N-type MOSC2 and P-type WSC2. And then the ternary circuit was implemented by connecting the N-type transistor to this heterojunction transistor. If you look at the transient measurement, we can see the ternary logic state, and under illumination light, the intermediate state can be tuned. Please allow me to wrap it up. To overcome the limitation of the conventional semiconductor, we need the next generation semiconductor, and today we looked into the transition metal dichloride and their photosensing applications such as image sensor array, neuromorphic devices, and ternary circuits. Beyond Moore's law, the era of artificial intelligence is coming. So I'm sure that these technology will be a great alternative for the next generation photonic applications. Thank you all very much.
Okay, thank you for nice talk, Dr. Hong. Is there any question from the audience? Okay,
Can I ask a
Professor
question?
Delbella? Yeah, sure.
Sungin, it was very nice talk, a very good introduction. I really like how you motivated the talk. I guess I have one technical question regarding your ternary logic. right? I mean, I know that people like to make this argument that ternary logic can be low power, but if you look at the inverter curves or just the transfer characteristics, right, the low power consumption actually comes from the fact that at a zero gate voltage, there should be very little or no current flowing through, right? But in the ternary logic that you present, right, there is actually a maximum current closer to zero voltage. So, I'm trying to understand whether how does this power consumption number, which is 1,000 times lower, come? Is it from some other types of operation or a new type of algorithm people are implementing? Because from the IV curves, it is clearly not low power consumption.
Yeah, I agree with you. In this case, there are the power, I think, but as far as I know, if we design a ternary circuit by using the binary semiconductor, there are almost 12 transistors. But if we use the heterojunction by using the TMD, we can reduce the scale or the power, the total power. So in this case, our my research is need the high power, but for the future, I expect the tuner circuit based on TMD will be operated by using the very low power, because the 12 transistor to conversion convert the 12 transistor to one transistor based on the ternary the heterojunction transistor.
Okay, yeah, I see your point.
Okay,
Thank
is there any other question?
Yes, I have one question
Okay,
about
please go
the
ahead.
photosensory adaptation. You have mentioned about the frequency switching. So, what is the main role of switching of these pulses in the photosensory adaptation?
Oh, I'm so sorry. Can you say that again louder?
Yeah, what is the main role of switching the pulses of light in the photosensory adaptation? That is the main question.
Sorry, I'm so sorry, but I cannot understand what you are
Yeah,
saying.
I'm saying that what is the main role of switching the light in
Yeah.
photosensory adaptation?
Yeah, that's a very good question. For demonstrating the behavior of the dark adaptation is just a constant light. But I want to show you the device performance more. So I just using the frequency. If we induced what I want to say is if we use the frequency temporal light, this device can be operated as well. That is my point. So simply for emulating human dark adaptation, it's just need the constant light. But
Yes.
I just suggest the additional result for the supplementary.
Thank you.
Okay, thank you for the nice presentation, Dr. Hong. Okay, let's wrap up our morning session. So we're gonna have a lunch break and then start the afternoon session from 1 p.m. We have multiple outstanding speakers in the afternoon session as well. So please participate in the afternoon session. Okay, thank you for coming to the morning session and see you in the afternoon session. Okay, thank you.